Welcome one more time.
This meeting is being recorded.
And sorry for this introduction because there were some internet connectivity issue from Professor Mandir Singh's end. However, thanks to Professor Rajesh Sharma, who is also one of the organizers, and so he will speak on numerical range matrices. And Rajesh, please, so start. Rajesh?
Yes,
Yeah.
I am.
Yeah. It's a bit louder, Rajesh.
Yes. Oh,
Yeah.
yes, this is on numerical range. The term numerical range was first coined by Stone 1932. It is also known as the field of values of the matrices. Its study provides insight into the structure of matrices. It also provides information about the eigenvalues of matrices. The unitarily similarity has several common properties. The numerical range of unitarily similar matrices is also same. We study all these properties in detail here. Yes, first notations and preliminaries. We begin with very simple definitions. An M by N matrix over the field C is a function A from the set of pair of integers into the field C. Field we take to be the complex numbers. It is, however, more convenient to describe matrix as an M by N array of scalars from the field C, consisting of M rows and N columns. For example, this 1, 1 goes to A, 1, 2 goes to B, and so on. Also, if M is equal to N, the matrix is said to be square matrix. And we denote the set of all complex N by N matrix by this symbol, Mn. Matrices with a single column are called column vectors, and they are denoted by Cn. For example, the size of the matrix is 3 by 3 when we study dynamics of rigid bodies. It is 6 by 6 in continuum mechanics. And it is around 20 by 20 in some problems related with economics. And it could also be 1000 by 1000 in oil exploration problems. It could be million by million also in internet connection problems. In quantum information theory, 2 by 2 matrices are also important, known as qubits. So the order of all matrices are of importance. This is just historical remark. In 1851, James Joseph Sylvester introduced this term after the Latin word worm. Now, eigenvalues. If A is a square matrix and lambda is a complex number, and we have a non-zero vector x belongs to Cn. And if we have this equation, Ax is equal to lambda x, then lambda is eigenvalue of A, and x is called eigenvector of A associated with lambda. The pair lambda x is called eigenpair. The set of all eigenvalues is called the spectrum of the matrix, and we denote it here by sigma A. Now, the important part here is that we can choose x to be unit vector. Why? Because we can write x as this column vector, x1, x2, xn transpose, and x star is conjugate transpose of x. Then x star x is x1 conjugate, x2 conjugate, xn conjugate, then multiply with this. We get mod x1 square plus mod x2 square plus mod xn square. Since x is not equal to 0, therefore this x star x is strictly greater than 0. So we can divide both sides in equation ax is equal to lambda x by root x star x root x star x. Now put this to be y. X over x star x to be y. Then we have ay is equal to ay. But here note that y is a unit vector. Y is a unit vector. Why? Because y star y is x star over root x star x, and multiply with same, we get 1. The point here is that we can assume in this equation ax is equal to lambda x, that x is a unit eigen vector. Now, equivalently, eigenvalues, this equation ax is equal to lambda x has a non-trivial solution if determinant of the coefficient matrix is 0. And this determinant a minus lambda is equal to 0 gives a polynomial, nth degree polynomial when a is a matrix of order n. And by fundamental theorem of algebra, then it has n eigenvalues. So if we have a matrix of order n, we have corresponding n eigenvalues. It is difficult to calculate eigenvalues of the matrices in general, but some information about the eigenvalues of some special type of matrices is known. For example, diagonal and triangular matrices, as we know, have eigenvalues on their main diagonal. The eigenvalues of idempotent matrices are 0 or 1. Idempotent matrices are those for which a square is equal to a. Therefore, lambda square is equal to lambda, and this gives lambda is equal to 0, 1. The eigenvalues of nilpotent matrices are all 0. A matrix is nilpotent if a raised to the power k is equal to 0 for some positive integer k. And this means lambda raised to the power k is 0. So all lambdas are. Now this those stochastic matrices are those for which row sum is equal to 1. All the elements of the first row, this comes out to be 1. Similarly for second row, third row, and so on. And in this case, one eigenvalue is 1. Why? Because, for example, we take this matrix, and 1, 1, 1 is always eigenvector. Why? Because sum here 2 plus 4 plus 3, 9, and 6 plus 2 plus 1, 9, 5 plus 1 plus 3, 9. So this is a eigenvector. Why? Because this multiplication is equal to 9, 9, 9, and take 9 outside, then this is a eigenvector. So for row stochastic matrix, one eigenvalue is 1. And this is well-known result. All the eigenvalues of a Hermitian matrix lie on real axis. Historically, Cauchy proved this in 1820. And Charles Hermite proved this in 1855 for Hermitian matrices. Also, for which U star U is equal to identity. And all the eigenvalues of this unitary matrix lie on the unit circle. That is, mod of each eigenvalue is 1. And this is proved by Brodsky in 1855. The eigenvalues of a skew-symmetric matrix is either 0 or purely imaginary. Now, Hermitian matrices are those for which A star is same as A. So if we have this equation AX is equal to lambda x, then multiplying with x star, because AX is also a vector belonging to Cn. So multiply with x star, we have this equal lambda x star x, which is lambda. Why? Because x is, we are taking unit eigenvector. Taking conjugate both sides, x star AX star is lambda conjugate. So x star A star x is lambda bar. So both are equal. Since left hand side are equal, therefore x star lambda is equal to lambda bar. So this means lambda is real if A is Hermitian. Now, if U is unitary, we take Ux is equal to lambda x, take conjugate transpose both. X star U star is lambda conjugate x star. Now multiply these two, we have this equation. but U is unitary and U star U is identity. Therefore, from here x star x is also 1, therefore mod lambda is 1. Now a matrix is Q Hermitian if and only if iota is Hermitian, and eigenvalues of Hermitian matrix are real, so it follows that eigenvalues of Q's Hermitian matrix are all purely imaginary number. This is also an important matrix known as circulant matrix. Its first row is this: C naught C1 Cn minus 1, and then start with Cn minus 1 and then C naught up to Cn minus 2, that is moving in this direction, and so on. Then the last row is C1 C2 up to C naught. Note that C is a normal matrix. A matrix is normal if A conjugate transpose is same as A conjugate transpose A. Now write omega is equal to cos 2 pi by n plus iota sine 2 pi by n. Then all the roots of z raised to the power n is equal to 1 can be expressed as omega naught is equal to 1, omega 1 is equal to omega, and so on. Then all its eigenvalues can be written in this form: j is equal to j varies from 0 to n minus 1. This equal sum I 0 to n minus 1 ci wj raised to the power I. Also eigenvectors are known. They are lambda xj is equal to 1 omega j square, so on up to omega j raised to the power n minus 1. And this can be verified by this equation. Also, we are going to use diagonalizable matrices. We start with the definition of similar matrices. Two square matrices A and B of same size, that is, they have same order. They are similar if there exists invertible matrix S, such that B is equal to S inverse AS. Also, a matrix is said to be diagonalizable if A is similar to a diagonal matrix. This means there exists an invertible matrix S such that S inverse AS is diagonal matrix. And then it is clear that all the diagonal entries are the eigenvalues of the matrix. Also, we have a special type of similarity called unitarily similar matrices. Two matrices are unitarily similar if there exists a unitary matrix U such that B is equal to U star A U. U is a unitary matrix, means that U star U is equal to U star is equal to identity. And then a matrix is said to be unitarily diagonalizable if A is unitarily similar to a diagonal matrix. So this is similarity and diagonalizable matrices. Now this is very important result, short triangularization theorem, very basic theorem in matrix theory. This theorem says that if we have any square matrix, then there exists a unitary matrix U such that U star AU is upper triangular. And then diagonal entries are eigenvalues. And further, we can choose unitary U such that we can take eigenvalues in any prescribed order. And this is called short triangularization theorem. Now, next is related theorem is spectral theorem. Now, the question is that not all the matrices are diagonalizable. Further, every diagonalizable matrix need not be unitarily diagonalizable. So, what are matrices which are unitarily diagonalizable? Only normal matrices are unitarily diagonalizable. And this is the spectral theorem. This means that there exists a unitary matrix U such that U star AU is diagonal lambda 1, lambda 2 up to lambda n is equal to D say. And then lambda 1, lambda 2, lambda n are eigenvalues. Converse is also true. That is, a matrix is normal if and only if A is unitarily diagonalizable. Now note one more thing is that from this theorem, we can deduce that A can be written as lambda 1 P1 plus lambda 2 P2 plus lambda n Pn. Lambda 1, lambda 2, lambda n, they are all eigen values. PIs are orthogonal projections. Orthogonal projection means first they are Hermitian, Pi star is Pi, they are positive semi-definite. At present, take positive semi-definite matrices to be those matrices which are Hermitian and their eigenvalues are non-negative. Now, second, Pi, Pj are orthogonal. I not equal to j. That is, Pi multiplied with Pj is 0 matrix. They are also idempotent. Pi square is Pi. And some Pi is equal to identity matrix. This follows from this above spectral theorem. We explain this how it follows only for n is equal to 3. Arguments are same for general case. Now, since A is unitarily diagonalizable, therefore we can write A U star AU is equal to diagonal matrix D. Then multiply in left by U and in right by U star, we have A is equal to UD U star. Using U star and U star U are identity. And D is diagonal now, so A can be written as U on diagonal eigenvalues, then U star. Also now write this matrix as sum of these matrices. Lambda 1, other are 0, and here second entry lambda 2, other are 0, lambda 3, other are 0. So now take U star inside, we have this matrix. We can also take by scalar multiplication lambda 1 outside. So we have this matrix. Now put this U and then in bracket 1 0 0 0 U star, this equal to P1 and U 0 0, this second as P2 and third as P3. Then we show that the above conditions are satisfied. P1 is this matrix, U inside 1 and other are 0, U star. P1 square is, then we calculate multiply P1 with P1. We have here U star, then U. So U star U is identity. Now multiply these two matrices 1 0 0 and 1 0 0. We get same matrix. So P1 square is P1. That in the same way, all PIs are idempotent. Now we see P1, P2. P1, P2, when we multiply, again U star U is identity. But if we multiply these two matrices, 1 0 0 and other is in A22 position, 1 others are zeros. Product of these two is 0. So P1, P2 is 0. Similarly, P1, P3 and P2, P3 are 0. Now we show that they are Hermitian projections. Pi star is taking conjugate transpose of this. This goes to this side, U star star, which is U. Then writing this middle matrix and then U star. This is same as P1. Similarly for other projections. Now we also have to show that they are positive semi-definite. Note that A is positive semi-definite if and only if X star AX is also positive semi-definite for all X belongs to square matrices. So from here we have P. This matrix is positive semi-definite. 1 0 0 0 0 0 0 0 0. This matrix is positive definite. Why? Because it is Hermitian matrix. And second, its eigenvalues are 0 0 1. That is non-negative. So this is positive semi-definite, and then U of this matrix, and then U star is also positive semi-definite. So in this way, if we write A in this form, then note that a Hermitian matrix looks like this. In diagonal entries, we have convex combinations of eigenvalues. Why? Because P1 plus P2 plus P3 is equal to identity. Therefore, first entry of capital P1 plus first entry of sec P2 plus first entry of P3. This sum is 1. Similarly, other diagonal entries are convex combinations of eigen values. Now we come to our main topic. These are just notations and some preliminaries which we are going to use in our discussions. Now, numerical range. Now, the standard inner product on Cn of any two vectors x, y is sum xi, yi conjugate. And this can also be written as y star x, where y star denotes the conjugate transpose of y. Also, if we have any element A belonging to Mn, then Ax also belongs to Cn. So Ax in a product Y can also be written as y star Ax. Now, associated norm x square is x star x. And this comes out to be sum I12 and mod xi square. Now, definition of numerical range. This is also known as field of values of matrices. First of all, A is any square matrices. Then its numerical range is the set of all x star Ax. But A is a unit vector. That is, its norm is 1. This means x star x is 1. Now, it is slightly lengthy to calculate numerical range of even very simple matrices. We explain this by this example. If we take A to be this matrix, take X to be this vector Z1, Z2 belonging to C, X belongs to C2. Then Z X star AX, this comes out to be Z2 star Z1 plus Z1 star Z2. Also note that X is a unit vector. Therefore, X star X is 1. This means mod Z1 square plus mod Z2 square is 1. Now take Z is equal to real part Z plus imaginary part, similarly Z1 and Z2. Then we see that Z comes out to be this expression. So this means it is only a real, so real part of Z is this term and imaginary part of Z is 0. Also, real part Z mod is then, by using triangular inequality here, we have 2 mod x1 mod x2 plus mod y1 mod y2. Now this is less than equal to x1 square plus x2 square. Why? Because x1 mod x1 minus mod x2 whole square is greater than equal to 0. From that, this follows. Similarly, this second follows. So this is 1. Why this is 1? Because Z is a unit vector. So real part of Z is less than equal to 1 and imaginary part is 0. This means numerical range in complex plane lies on real axis and mode of real part of Z is less than equal to 1. So WA is a straight line segment joining, is a line segment joining -1 to 1. Because imaginary part is 0 and real part varies from -1 to 1. So this example shows that it is lengthy to calculate the numerical range of even very simple matrices, 2 by 2 matrices. Take this second example, A is equal to A minus A minus A. For this, we calculate in the same way, X star AX comes out to be this expression. Now taking mod, and then mod comes out to be this expression, and then this, since imaginary part of a complex number is less than equal to its modulus. So we have this first inequality here. Also note that the term inside under root is mod Z1 square plus mod Z2 square whole square, which is 1, because Z is X is a unit vector. So numerical range is mod Z is less than equal to mod A. This means numerical range is a disk centered at origin and radius mod A. We now discuss some properties of numerical range. First is compactness. take A to be any square matrix, then the numerical range is a compact subset of C. Why? For any A belonging to Mn, we said WA is the range of the function fx is equal to x star ax. WA is defined as x star ax over unit vector x star x is equal to 1. So what is the domain? Domain is set of all x belongs to Cn, x star x is equal to 1. So it is the surface of Euclidean unit ball and is clearly a compact set. Also note that if we put here A is equal to Aij, that is entries, then we find that this fx is this expression. And this is just a quadratic form in xi and xj. And this function is a continuous function. Also, mapping of continuous compact function is compact. So we see that numerical range is a compact subset of C. By compactness, we have a useful consequences that it always contains its boundary, because it is bounded one thing, and second, it is closed. So by close, we have that numerical range always contains its boundary. Also, since this Euclidean unit ball is connected set and continuous function takes connected set to connected set, therefore numerical range is a connected set. And we will see in further discussion that it is actually simply connected. That is, each point is filled up by the values of x star a x. Now, second property, translation. Numerical range of A plus Zi is equal to numerical range of A plus Z. Zi mean we have here a scalar matrix Zi, and then this comes out to be numerical range of A plus Z. That is the numerical range of A plus a scalar matrix is just numerical range of A plus it is translated, or you can say displaced to some other position. Now, proof of this, the sum of two subsets of x and y is defined like this. Set of all x plus y such that x belongs to x and y belongs to y. So numerical range of A plus Zi is equal to x star A plus Zi x. X is a unit vector. And this can be written as x star ax plus x star zx. Z can be taken outside, and using x star x is equal to 1, this equal x star ax plus z. So this is of the form w plus z, where w belongs to numerical range of A and z belongs to singleton set. So this is just equal to wa plus z. Next property is scalar multiplication. For all A belonging to Mn and Z belongs to C, numerical range of Z is equal to Z numerical range of A. So what is the meaning of it? If we multiply A with some scalar Z, then the numerical range of A is multiplied with Z. This means either numerical range is rotated, contracted, and or expanded. So this is simple by definition. Numerical range of Za we can write in this form, and then this equal Z x star ax. X star ax is any element of numerical range of A. So this equal ZWA. Now this next property is important, spectral containment property. The spectrum of a matrix is contained in numerical range. Spectrum is the set of all eigenvalues. Now, since numerical range has elements of the type x star ax, x star ax, and in this expression we can choose x to be eigenvector of A. Then this comes out to be x star lambda x, and since x is unit eigenvector, this is simply lambda. So every eigenvalue is in numerical Now next important property, projection property. In A matrix, we take this matrix, called Hermitian part of matrix. H A is equal to A plus A star by 2. And then a real part of numerical range of A is just real part of Z. Z belongs to numerical range of A. This is equal real part of X star AX. X is unit vector. Then this projection property says that numerical range of Hermitian part of A is same as real part of numerical range. Now proof is simple. Numerical range of Hermitian part of A can be written like this. X star of A plus A star by 2 X. X is a unit vector. Now this equal half X star AX plus X star A conjugate transpose X. Now this is just a number. We can take its conjugate transpose. And then we have this equal X star AX conjugate. And this is real part of X star AX. X is a unit vector. This is real part of numerical range. Now, what we are doing is that this property says that this is the numerical range. So what is real part? This distance P to Q on real axis. And this property says that this also equal to numerical range of A plus A star by 2. Similarly, we can take in imaginary part K A this matrix A minus A star by 2 iota. Then imaginary part of W we take this set. Imaginary part of Z, Z belongs to numerical range of A. Then numerical range of this K A is same as imaginary part of numerical range of A. This has same proof, same calculations. So what we have according to this Cartesian decomposition, A is A plus A star by 2 plus iota time. This is Hermitian part, A minus A star by 2 iota. Numerical range of A is numerical range of Hermitian part plus iota time numerical range of this imaginary part. Now next property is positive definite indicator function. Now we denote the upper half plane of complex plane by this RHP. This equal Z set of all Z belongs to C. Real part of Z is greater than 0. Here we have excluded the imaginary axis. And in closed right half plane, we denote it by RHP naught. And in this, the real axis is included. Now we have this positive definite indicator function. If numerical range is in right half plane, then A plus A star is positive definite, and conversely. And this is clear from this diagram. If numerical range is in right half plane, that is WA is in right half plane, then by projection property, this PQ is also equal to real part of WA. So PQ is also in right half plane. This mean eigen values of A plus A star by 2 are also in right half plane, means they are positive. Also A plus A star by 2 is a Hermitian matrix. So A plus A star is positive definite. Conversely, if A plus A star is positive definite, then numerical range of A plus A star by 2 is in right half plane. Its real part by projection property is also in right half plane. So this, when real part of numerical range is in right half plane, then numerical range itself is in right half plane. Now similarly, we can have upper half plane. We can consider upper half plane. Open upper half plane is set of all Z belongs to C. Imaginary part of Z is greater than 0. And in closed upper half plane, imaginary part of Z is greater than equal to 0. So we have similar type of results. Numerical range is in upper half plane if and only if A minus A star by iota is positive definite. And it is a open upper half plane if this A minus A star by iota is positive semi-definite. Now sub-additivity. Next property, for all AB belonging to V, Mn, we have numerical range of A plus B is contained in numerical range of A plus numerical range of B. We have this set, numerical range of A plus B is this set, x star AX plus x star BX. X is unit vector. And numerical range of A plus numerical range of B, x star AX, x unit vector, y star BY, y unit vector. Now note here that we are repeating here x. Here we can also repeat x, but can also put other values of y. So clearly this set, numerical range of A plus B, is contained in numerical range of A plus numerical range of B. On the other hand, numerical range of A plus numerical range of B is not always contained in numerical range of A plus B. We take this example 2, 0, 0, 0, B this matrix, and A plus B is this matrix. Now we will discuss later and also in tutorial classes that numerical range of this matrix, diagonal matrix A, is interval 0 to 2. And for this interval 0 to 3. While for A plus B is interval 2 to 3. So WA plus WB is 0 to 5. Clearly this is WA plus WB is not contained in W of A plus B. Now next property, unitary similarity invariance property. This is very important property, and as we are going to use in many theorems. A square matrix, U also square matrix of same order and is unitary. Unitarily similar matrices have same numerical range. This is very important. Unitarily similar matrices have same numerical range. We prove this. Let Z be an element of A. Then Z can be written as Y star AY. Z we are taking element in numerical range of A. So Z is equal to Y star AY unit vector. So Z is equal to Y star AY. Now we can put here identity matrix. UU star is identity. Here also UU star identity, and this can be written in this form. Now take this X is equal to U star Y. So this can be written as X star U star AU X. Now X star X, we calculate this. This also comes out to be 1. So this Z is then element of numerical range of U star AU. So we have numerical range of A is contained in numerical range of U star A. Conversely, take Z to be any element of numerical range of U star AU. Then Z can be written in this form where Y is unit vector. Now put Uy is equal to X. So this comes out to be X star AX. Also X star AX we calculate from here. This is again 1. So this is an element of numerical range of A. So numerical range of U star AU is contained in numerical range of A. So combining these two results, we have this important property: numerical range of U star AU is same as numerical range of A. Now a related property is isometric projection. Now what is isometry? If A belongs to Mn and let K is less than equal to order of this matrix, then P belongs to Mn K is isometry if P star P is equal to identity. And we can see this P star P belongs to Mk. That is P star P is a square matrix of order K. Then P is called isometry and P star AP is isometric projection. So next property is isometric projection property. If P is n by K matrix, With orthonormal columns, this means that P is isometric. Then numerical range of P star AP is contained in numerical range of A. And this has similar type of proof as in case of unitary similarity invariance property of numerical range. Because if Z belongs to numerical range of P star AP, then for some unit vector X, this can be written as X star P star AP X. This comes out to be Px star APX, and this equal Y star AY. And we calculate that Y star Y is equal to 1. So Z is also in numerical range of A. So we have this property, numerical range of P star AP is contained in numerical range of A. For example, take P to be this matrix, P0, 0, 1, 0, 0. This is isometric. If we calculate P star P, this comes out to be identity matrix of order 2 by 2. Let Aij belongs to M3. These are entries of A. Then we calculate P star AP. This comes out to be this matrix, this top left matrix A11, A12, A21, A22. So from this, we also see that the numerical range of this principal submatrix is contained in numerical range of A. Similarly, for other isometries, we can consider this isometry. We have this expression is other principal submatrix. Similarly, we have here other cases. Now, this submatrix inclusion property, this we are also going to use in some theorems. A belonging to Mn, this is a square matrix, and let Z be any proper subset of this index set 1, 2 up to n. Then Az denotes the principal submatrix, which is whose entries are in the rows indicated by J and also in the columns indicated by J. Then Aj is a principal submatrix of A, and every principal submatrix of A can be written in this form. Now, submatrix inclusion property. The numerical range of any principal submatrix is contained in numerical range of A. We have to show that numerical range of Aj is contained in numerical range of J. The point here is that Aj defines the principal submatrix whose entries are in the rows indicated by J and in the column indicated by J. Now we take Xj to be that unit vector in which we have non-zero values only on the position indicated by J and others are 0. Then we calculate X star J Xj is equal to 1, and this comes out to be X star Ax. This proves this property. We explain this by one particular case so as to make it visible. Take Aj, this principal submatrix A11, A12, A21, A22. Take Xj, this, because here J is 1, 2. So take these non-zero X1 and X2 and all others are 0. Then we calculate and take Y to be this column matrix X1, X2. Then Y star Y take 1. So this also gives X star J Xj is equal to 1. So Y star AJY, we calculate this expression, this comes out to be this. Now we calculate X star J A. Here we are calculating with Aj, but here with A. And this also comes out to be this expression. So these 0 zeros are making these columns and row not contributing to this sum. That is why numerical range of every principal submatrix is contained in numerical range of A. Now, next we come to convex combination. If we have n numbers, either on straight line or plane, then by convex combination of these numbers u1, u2, un, we mean an expression of the form p1 u1 plus p2 u2 plus on up to pn un. And what are PIs? PIs are non-negative real numbers such that their sum is 1. Then we say this expression is convex combination of UIs. Also, a convex set in complex plane is a set is convex if we take any 2 points on that set. Then line joining these two also lies on X. These are some points from geometry. Also, the convex hull of a set X of points is the smallest convex set that contains X. Also, we define convex hull of these points, Z1, Z2, Zi. Convex hull of these points is some Pi, Zi. Pi's are non-negative, sum Pi is equal to 1. This means this convex hull is just all possible convex combinations of Z. We can take Pi any non-negative and such that their sum is 1. This is from geometry. The convex hull of finite point set in C forms a convex polygon. Also, the convex hull of a set A is also defined as this in parametric form Tz1 plus 1 minus Tz2. Z1, Z2 are any 2 points in X. This means the convex hull consists of all line segments between points in C. Why we are defining them? Because we are going to use these terms in next property. Let us consider the case, simplest case, diagonal matrix. Numerical range of a diagonal matrix, convex hull of its diagonal entries. D to be this diagonal matrix and calculate X star D X. This comes out to be expression of this form. Xi square are non-negative. Also, since X is a unit vector, some Xi square is 1. So what we have, this is convex combination, and we have to take this convex combination over all unit vector X. So this is convex hull of the diagonal entries. Conversely, let we have an expression of this form, that is convex hull, a convex combination of diagonal entries. Then we can choose X star to be this root P1, root P2, root Pn. Then X star X is 1. Why? Because this sum Pi is 1. So X star dx is again this convex combination is in WD. Now normality, next property. Suppose we have to find the numerical range of a normal matrix. The numerical range of normal matrix is convex hull of its eigenvalues. This follows from the last property and unitarily similarity invariance property. Because by unitarily similarity invariance property, numerical range of A is same as numerical range of U star AU. And by spectral theorem, we can choose unitary U such that U star AU is diagonal matrix. And also diagonal entries are eigenvalue. So by last property, numerical range of this normal matrix is the convex combination of convex hull of the eigenvalues. So one more special case of normal matrices is Hermitian matrix. The numerical range of a matrix is real line segment if and only if A is Hermitian. That we have seen, if A is Hermitian, the eigenvalues are all real. Also, Hermitian matrices are normal matrices because they satisfy A star A is equal to A star. So numerical range is convex hull of the finite set of points in on real axis. Hence, numerical range is a real line segment. Conversely, suppose WA is a real line segment, that is segment on real axis. Then X star AX is real for all X, and we have to show that A is then Hermitian. Take this vector X plus Y star AX plus Y. This also belongs to C, and therefore this expression is real. we calculate this comes out to be this expression, just simple multiplication. Now x star ax is real, y star ay is also real. So this first expression is real and in left hand side real. So this expression x star ay plus y star ax must be real. Now we use this expression to show that A is Hermitian. Now take this matrix AX, this column matrix X is equal to EK. This is a column vector in which at kth position we have entry 1 and all other entries are 0. Then we calculate x star ay comes out to be akj and y star ax comes out to be ajk. Now since this left hand side is real, therefore this expression is also real. This mean imaginary part is 0, which gives imaginary part of akj is minus imaginary part ajk. Now take x is equal to iota ek and y is equal to ej. Then we have this expression x star ay plus y star ax equals to minus iota akj plus iota ajk. Again, this left hand side is real, so we have real part of akj is equal to real part of ajk. So we can write akj is equal to ajk conjugate. And this is the definition of Hermitian matrix. Now, further extension of Hermitian matrix is essentially Hermitian matrices. Essentially, Hermitian matrices are those matrices which can be written in this form: alpha h plus beta I, where h is Hermitian matrix. First, note that essentially Hermitian matrices are normal matrices. Why? Because A star A, we calculate this expression. This is same as A star. Also, 2 by 2 normal matrix is essentially Hermitian. Why? Because by spectral theorem, as we have discussed, A can be written in this form: lambda 1 P1 plus lambda 2 P2, where PIs are orthogonal projections. That is, they are Hermitian and their sum is identity. Now using this, P1 plus P2 is equal to I here, substitute value of P2 is equal to I minus P1. We see that A can be written in this form. So here lambda 1 minus lambda 2 is a complex number, then this projection P1 is a Hermitian matrix, then again complex number. So A is essentially Hermitian. That is, 2 by 2 normal matrices are essentially Hermitian. Further, what are essentially Hermitian matrices? They are normal matrices. And those normal matrices whose eigenvalues lie on some real line segment. Why? Because suppose first A is normal and its eigenvalues lie on a straight line. Then we can write its eigenvalues as real part plus imaginary part. Since eigenvalues are on real axis, imaginary parts lie on some straight line like y is equal to m1x plus c. So we write imaginary part in this form. So then lambda IA, we calculate this can other direction we can also write like this. If we take imaginary part and then take equation x is equal to my plus c. Now for some unitary u, it then can be written as u star, this diagonal matrix, and u. And now substitute values of lambda I a from here. And this expression comes out to 1 plus iota c, where B1 is this matrix U star and in diagonal only real parts of eigenvalues, then U. So if we calculate B1 star, this comes out to be U star, and then again diagonal this remains same because we have real diagonal entries, and then U. So B1 here is Hermitian. So this means if eigenvalues are on the straight line, then A is essentially Hermitian. Conversely, if the matrix A is of this form, A is equal to alpha h plus beta I. This is essentially Hermitian matrix. Then its eigenvalues are of the form alpha eigenvalue of h plus beta I. Now we know that this transformation corresponds to when we multiply with a complex number. This means that all the eigenvalues are rotated and contracted or expanded and then translated. So the real axis is translated to some other straight line. So if A is essentially Hermitian, then its eigenvalues are on the straight line. Also A must be known. Now this theorem, if A is a square matrix, then its numerical range is a line segment or a point if and only if A is essentially Hermitian. If A is essentially Hermitian, this can be written in this form, where H is Hermitian matrix. Then numerical range by using translation and scalar multiplication property can be written in this form. So is a line segment. WH is a line segment. Conversely, let numerical range of A is line segment. Then numerical range of A, we write it this form 1 minus t z1 plus t z2 in parametric form. That is line segment joining z1 and z2. Now by translation property, instead of A, we take this matrix A minus z1 I. By translation property, this is for WA minus z1. Subtracting here z1, this comes out to be t z2 minus z1. T lies in this interval 0 to 1. Now z2 minus z1 is a complex number. We write it in polar form. So write here r exponential iota theta t. Exponential iota theta t we can take outside, and then by cross multiplication we here have exponential minus iota theta, and we can take it inside by using scalar multiplication property. So what we have, numerical range of this matrix exponential minus iota theta A minus zi is this real line segment. On right hand side we have only real terms. So if the numerical range is real line segment, we have shown that the matrix is Hermitian matrix. This means exponential minus iota theta A minus zi is a Hermitian matrix. So from this we calculate A is equal to exponential iota theta plus z1 is essentially Hermitian. Now we come to discuss the convexity of numerical range of matrix. For this we start by showing that numerical range of 2 by 2 matrix is a convex set. For this we need some simple properties, and we study them as lemmas. Lemma 1, Aij belongs to M2, that is A is a square matrix of order 2. Then alpha and alpha is any complex number in its numerical range. Then there exists a unitary matrix U such that alpha is 1, 1 and 3 of U star AU. So what is the meaning? If we have a 2 by 2 matrix and its numerical range, then from that numerical range we can choose any complex number to be 1 by 1 entry of a matrix which is unitarily similar to original matrix A. How? Suppose alpha belongs to numerical range. X belongs to E, alpha is x star AX. So if we take x to be this column vector x1, x2, then alpha is this complex number we calculate from here. Now we take unitary to be this matrix x1, x2, and then x2 conjugate minus x1 conjugate, and then calculate U star U, which comes out to be identity. So this is a unitary matrix, and for this unitary matrix U star AU, we calculate this. This comes out to be same as alpha. We need this lemma just for 2 by 2 matrices. In fact, this is true for all matrices, that is matrices of all order. We will discuss this in tutorial section. Now, second lemma, if A is 2 by 2 matrix, then there exists a unitary such that two main diagonal entries of U star AU are equal. This mean U star AU are equal mean if two entries are A11, A22, then we can choose U star AU to be the matrix whose both diagonal entries are equal. Let A belongs to M2 and B be this matrix. A minus trace A by 2I, then trace B is equal to 0. And for any unitary matrix, U star AU is equal to U star BU plus trace A by 2U. So the diagonal entries of U star AU are equal if and only if diagonal entries of U star BU are equal. Since trace of U star BU is same as trace of B, we calculate this comes out to be trace A minus trace A by 2. Trace identity is 2. So trace of B is 0. So we can suppose that trace of A is 0. So what is happening? This matrix A11, A12, A21, A22. We can write this matrix in this form because just we are adding this. So we have same here A11. So we have to show that A11 is equal to A22. So if these two are equal, then we are just adding A11 plus A22 here, A11 plus A22 here. So if these two are equal, then these two must be equal. But they are negative of each other. So they are equal only when both are 0. So without restricting generality, we may assume that trace A is 0. So it is enough to show that one entry of U star AU is 0. Why? Because then by using last lemma, we can find a unitary such that one entry of U star AU is 0. By lemma 1, we need only to show that 0 is in numerical range of A. Now, since trace A is 0, its characteristic polynomial is of the form x square minus trace A plus determinant of A is 0. So its eigenvalues are of the type alpha and minus alpha. So if alpha is equal to 0, then clearly it lies in the numerical range. If alpha is not equal to 0, then the unit vectors x and y correspond to eigenvalues. Alpha and minus y are linearly independent. Why? Because they are distinct eigenvalues and eigenvector corresponds to distinct eigenvalues are linearly independent. W is equal to exponential iota x plus y. We take this vector, then this is not equal to 0 for any theta because x and y are linearly independent. And we take u to be this unit vector w over root w over norm w. Then we calculate u star AU. This on calculating comes out to be this expression. Here imaginary part exponential iota theta y star x. Y star x is a complex number. And if we multiply it with another complex number, then we can choose second complex number to be that complex number such that the product is 0. So we can choose theta here such that u star AU is 0. So 0 is in numerical range. And then we can bring it to 1 position by unitarily similarity. Then both the diagonal entries are 0. So this is our lemma. Now next lemma. The numerical range of A is convex if and only if the numerical range of the matrix 0 A B 0 where A B are non-negative is convex. Note that W A is convex if and only if numerical range of A plus alpha is convex. Why? Because by translation property, numerical range of A plus alpha is numerical range of A plus alpha. So what we are doing, we are just translating it to some other position. So if something is convex, if some set is convex at one position, it is also convex at other position. So WA and WA plus alpha I are simultaneously convex. This we have explained mathematically here. Now we choose alpha is equal to minus trace A by 2. It follows that WA is convex if and only if B is convex, where B is equal to A minus trace A by 2, also trace B is 0. Thus, we may suppose that trace A is 0. Now use lemma 2. We can choose a unitary such that this matrix B is unitarily similar to a matrix of this type. Both diagonal entries are equal and they are CD some complex numbers. So ultimately, convexity depends upon this type of matrix where diagonal entries are 0 and often diagonal entries are complex. Now we have to make them real and non-negative, C and D. For this, we choose this unitary matrix 1, 0, 1 exponential iota theta of diagonal entries are 0. Then we calculate this U star U comes out to be this 2 by 2 identity matrix. And then take this U star AU. Calculate this. This comes out to be this matrix. Now C and D are complex. So we can write C is equal to mod C exponential iota theta 1, D is equal to mod D exponential iota theta 2. So we have this matrix. Now we choose theta is equal to theta 2 minus theta 1 by 2. So what we have 0, 0 here mod C exponential iota theta 1 plus theta by 2 and same quantity here. So we can take this common. So this we take common, we have 0, 0 mod C mod D. So psi is equal to theta 1 plus theta by 2 where. Now we calculate numerical range of this matrix. So this depends only on this matrix 0 mod C mod D mod 0. Why? Because this just corresponds to rotation. So convexity depends ultimately on such type of matrix for 2 by 2 case 0, 0 and of diagonal entries are non-negative. So what is the point in this lemma is that if we have to show that numerical range of any arbitrary 2 by 2 matrix is convex, it is enough to show that the numerical range of this matrix is convex, where A, P are non-negative real numbers. Now we calculate numerical range of this matrix. In next theorem, we calculate Z star AZ again using same arithmetic. We have this complex number is equal to B plus A, then this term plus iota this. So real part is B plus A x1 x2 plus y1 y2. Y is equal to this. Now we calculate this part 4x square over B plus A whole square 4y square over B minus A whole square. This comes out to all time mod Z1 square mod Z2 square. By using this mod Z1 minus Z2 square greater than equal to 0, this implies mod Z1 square greater than equal to this, and this is 1. Why? Because Z is a unit vector. So using this here, we have this numerical range, and this is an elliptical region. An elliptical region, that is a region inside ellipse including its boundary, and this is a convex set. And also note that in this the length of major axis of this ellipse is this a plus b by 2 minus a plus b by 2 a plus b. This is length of major axis, and length of minor axis is b minus a by 2. These are foci, and foci we can calculate these. Eccentricity comes out to be this once major axes are length of major axes are known. From this we calculate foci are plus minus root AB 0. So these are foci. Also distance from center OF1, OF2. This is root AB. Now we use this result to discuss now our main theorem, the numerical range of 2 by 2 matrix. Any arbitrary mean complex entries. A is 2 by 2 matrix. We write B to be this matrix A minus trace A by 2I. Then numerical range is a closed ellipse with its interior. It may be a degenerate ellipse. By degenerate ellipse, we mean that either a point or a straight line. So numerical range of arbitrary 2 by 2 matrix is either a point or a straight line or a disk or closed ellipse. Center is trace A by 2, and length of major axis is this. Trace B star B plus 2 determinant P power 1 by 2. P is this matrix. And length of minor axis is B star B minus 2 more determinant P power. The eigenvalues of A are foci of numerical range of A. Also, the eigenvalues coincides if and only if numerical range of A is a circle or point. Distance of foci from the center is determinant P power 1 by 2 with mode. The major axis passes through two eigenvalues. Now these 2 points, they are important, 9 and 10. The numerical range is a closed line segment if and only if A is normal. This is important. The numerical range of 2 by 2 matrix is closed line segment if and only if A is normal. This means if A is not normal, then it is not a closed line segment. That is, WA is then a non-degenerate ellipse, clearly including its interior, if and only if A is not normal. And also, this is important, eigenvalues of A are interiors of WA 10. In this case, when A is normal, eigenvalues are on the boundary. But when we have ellipse or disk, the eigenvalues are in the interior of numerical range of A. What is the proof of this? Proof of this is depending on the proof of last theorem. A belonging to M2 and B, we take this matrix. Then by translation property, WA is WB plus trace A by 2. Now we consider matrices which are unitarily similar to matrices B. And as discussed above, in above lemmas, numerical range of B A is then comes out to be equal to exponential iota phi, numerical range of this matrix 0 A B 0 plus trace A by 2, where phi is any real number. So we have calculated the numerical range of this matrix, numerical range 0 A B 0. On using, and also note that this matrix is unitarily similar to matrix B. This matrix B. So by using some invariant properties of unitary matrices, we can calculate some terms involving this matrix. Now first, the numerical range of this is closed ellipse with its interior. Now this transformation W is equal to alpha Z plus beta with mode alpha is equal to 1. This corresponds to pure rotation and translation. So when we take numerical range of A, this is just rotated. The numerical range of 0, A, B, 0 is rotated. That is, the ellipse, which was the numerical range of this matrix, was rotated and translated to this by this factor. So it remains an ellipse with its interior. The center of this ellipse W00 AB is 0. So center of this ellipse, this is just translation, is trace A by 2. Also, we have shown that the length of major axis of this for this matrix, the numerical range of this matrix is A plus B. Now we have to calculate this expression A plus B in terms of matrix B, which is unitarily similar to this matrix 0, A, B, 0. So we can express A plus B in terms of determinant of B and trace B star B. We have this matrix for this determinant of B is minus AB exponential iota to 5. This gives determinant of B mode is AB. Mode of exponential iota to 5 is 1. Why? Because this matrix is unitarily similar to matrix B, and similar matrices have same determinant. Also, trace B star is B in for unitarily similar matrices. So trace B star B is this expression. And from here we calculate A plus B. This comes out to be A square plus B square plus 2AB. And this equal from these two equations, trace B star B plus 2 mode determinant B half. So this is the length of major axis of arbitrary ellipse. Arbitrary ellipse means 2 by 2 ellipse with any complex entries. Also B minus A, then similarly we can calculate, this comes out to be trace B star B minus 2 mode determinant B power half. We have calculated the foci of this numerical range of this matrix R Z is equal to plus minus root AB. So these points are just shifted by this rotation factor exponential iota by and translated by this factor. Now we calculate eigenvalues of A and find that they also comes out to be again same. Hence the eigenvalues of A are foci of numerical range of A. Also the eigenvalues, these are the eigenvalues, they coincides if and only if determinant B is 0. It is clear from here because this involves plus minus sign. So when determinant B is 0, the eigenvalues coincide. And when eigenvalues coincides, length of major axis and minor axis remain same. Why? Because only difference is that major length of major axis trace B star B plus mode determinant B power half. So when determinant B is 0, this is trace A star, trace B star B power half. Similarly for minor axis, this is also trace B star B by half. Now distance of foci from the center of ellipse correspond to this numerical range of this is root AB, and root AB is mode determinant B power half. So for numerical range of A distance from center is mode determinant B power half. The major axis of any ellipse passes through its foci. Also, eigenvalues of A are foci of numerical range. It follows that major axis passes through the eigenvalues. Now, this is important. We are going to use in further discussion. We have shown that if A is any square matrix, then its numerical range is a line segment if and only if A is essentially Hermitian. We have also shown that every normal matrix of order 2 by 2 is essentially Hermitian. It follows that W is a closed line segment if and only if A is normal. Again, this next part we will discuss in tutorial section. It is also clear that numerical range is a single point if and only if A is a scalar matrix. Also, it is clear from 9 that then WA is a non-degenerate ellipse if and only if A is not a normal matrix. Also note that for this numerical range, that is ellipse correspond to this. A plus B by 2 is length of semi-major axis. And this is the distance from the distance of the foci from the center. So by using arithmetic geometric mean inequality, this is non-negative. And equality occurs if and only if A is equal to B. And in this case, this matrix becomes a normal matrix. So only when 2 by 2 matrix is normal, its eigenvalues are on the boundary. Otherwise, they are in the interior of numerical range. So here we have shown that the numerical range of 2 by 2 matrices are completely known. And also we have shown that this numerical range is a convex set. Now using this, we prove this main result. For this is called Topli's-Hausdorff theorem. Topli's proves this in 1918 and Hausdorff in 1919. For any A belonging to B, the numerical range of A is convex set. Yes, proof to show that numerical range of A is convex set, we have to show that the line segment joining points Z1, Z2 is also in numerical range of A. Equivalently, if Z1, Z2 belongs to numerical range, then Z1 is X star A X and Z2 is Y star A Y. If Z1 is equal to Z2, clearly there is nothing to prove. Suppose Z1 is not equal to Z2. If X and Y are linearly dependent, then we can write this as Y1 is equal to Y star Y mod C square X star X. This comes out to be mod C is 1. So in this case, Z2 is again comes out to be Z1. So if Z1 is not equal to Z2, then X and Y must be linearly independent vectors. And X and Y are linearly independent vectors, therefore we can find this vector space spanned by X and Y, which is a two-dimensional space. And it also has orthonormal basis. We take orthonormal basis V1, V2. So there exist complex numbers C1, C2, C3, C4 such that we can write X in this form and also Y in this form. That is X is C1 V1 plus C2 V2, Y is C3 V1 plus C4 V2. Then we also calculate this 1 is equal to X star X, substitute value of X star and this X, and use here norm V1 is 0 because V1 and V2 are orthonormal basis. So this mod C1 square plus C2 square is 1. And similarly, mod C3 square plus mod C4 square is 1. So if we take alpha to be this vector in C2 and beta this vector in C2, then they are unit vectors from here. Mod C1 square plus C2 square is 1. That is alpha star alpha is 1. Now we consider this isometry. P be the n by 2 matrix with columns V1 and V2. Since columns are V1 and V2, they are orthonormal, therefore P is isometric. So we now have P alpha. P alpha, we calculate this comes out to be X. Similarly, P beta, we calculate this comes out to be 1. Then Z1 x star x can be written as, in place of x, just write P alpha. And here P alpha star. So write this as alpha star P star. So this equal alpha star P star AP alpha. Similarly, Z2 can be written as beta star P star AP beta. Now note here that this P star AP is a 2 by 2 matrix. And we have shown that numerical range of 2 by 2 matrix is a convex set. So Z1 and Z2 belongs to these 2 by 2 matrices, P star AP, and also alpha and beta are unit vectors. So the line segment joining these two, since P star AP is a convex set, is in numerical range of P star AP. But numerical range of P star AP is contained in numerical range of A by isometric projection property. So ultimately, the line segment joining Z1, Z2 is also in numerical range of A. This shows that for any complex n by n matrix, its numerical range is a convex set. And this is very fundamental and most important property of numerical range, known as Topliss-Borsdorf theorem. Yes, Professor Sarkar, how many more time I can take?
Yeah, maybe if you are done, because 11:30 we start the second.
Okay, then yes, then participant can ask any question.
Yes, participant can ask some questions. Yes. Go ahead, ask your, if you have any question, please go ahead.
Hello, sir.
Yes.
Yeah, actually, we have seen that we don't have any relation between W of, if A and B are two different matrices.
Yes.
We have seen in general that W of A plus W of B is not necessarily a subset of W of A plus B.
Yes.
So is there any condition that we should put on A and B so that they will be equal or they will be contained in each other?
Yes, there is no such condition in literature. Any useful such condition. For example, translation property is there that we use, because here we have W of A plus alpha E is same as W of A plus alpha, but no other such condition is there.
So there is no conditions on A and B. Okay. Now one more question. The lemmas and theorem which you have proved is just for n is equal to 2 case.
Yes.
So in general, can we say same thing?
No, it is very difficult to say something about the numerical range of n by n matrices, as we will see in next talk. But for 2 by 2 matrices, we have first studied them because we are using these convexity of 2 by 2 matrices and numerical range of other properties of numerical range of 2 by 2 matrices to prove other properties of numerical range of n by n matrices. Yes.
Yes, sir. Okay. Thank you.